Do you have a team without an HR department? Or maybe your HR department is someone who just got the job because they were already in the office. Or maybe you have a well-staffed HR department and are just looking for outside professional advice. Whatever the case, HRTG can help. HRTG can help with handbooks, interactive training workshops, employee relations that include resolving issues and answering questions, performance reviews, and writing compliance and policies. To simply put it, they cover everything from hiring to retiring. Do what you're good at and let HRTG do what they are great at, help you with your HR needs. Go to scalinguph2o.com/HR to find out more. Welcome to Scaling Up, the podcast where we scale up on our knowledge so we don't scale up our systems. My name is Trace Blackmore. I am the host of Scaling Up H2O. And Nation, I am so excited because just around the corner, I am going to see so many of you because so many listeners out there in the Scaling Up Nation are also members of the Association of Water Technologies. So if you practice the same area of water treatment that I do, you are most likely a member of the Association of Water Technologies. And if you are, you know what I'm getting ready to tell you because the AWT convention, it was online last year, but it is in person this year, and I cannot wait to attend. It's going to be September 22nd through 25th in Providence, Rhode Island. And folks, I want to do something special while I'm there. I will announce that a little closer when we air the episode before the convention. So be listening for that. And we'll probably be doing a meetup, but I don't want to tell you everything until we get a little bit closer, trying to build some suspense. The bottom line is, if you're not there, you can't attend, so you want to be there. How do you do that? Well, two ways. You can go to our website where we post everything for you. You don't have to worry about taking notes during this show because we're going to have everything on the website, scalinguph2o.com, and we'll have links for you to go straight to AWT. But AWT site is not hard to remember. It's awt.org. Either one of those places will allow you to get registered so you can see me and I can see you, and we can just have a great time. Another event that is coming up for all you corrosion enthusiasts out there, is that a thing? Well, if it is, you know who you are. Get ready, Corrosion Technology Week. Yes, that is the NACE convention. That's going to be happening October 18th through 20th in Houston, Texas. This event is all about the latest standards, products, and services, all surrounding corrosion prevention and mitigation. If you are somebody that deals with corrosion like all of us do in industrial water treatment, check out NACE by going to their website. And of course, we will have that on our website so you can click right over there. Now, that's in October. And speaking of October, October is the water treater's favorite month of the year. Why is that, you might ask? Well, it's the month that contains the holiday just for us. And to tell us a little bit more about that, here's James McDonald.
The 4th Annual Industrial Water Week will be here before you know it. Coming this October 4th through 8th, now is the time to start planning how you will celebrate Pre-Treatment Monday, Boiler Tuesday, Cooling Wednesday, Wastewater Thursday, and Careers Friday. Some may still be asking, why should I celebrate Industrial Water Week? The answer's simple. Why not? Only a select group of people understand what we do, but the modern industrial world couldn't exist without us helping to safeguard water, equipment, energy usage, environmental impact, and the bottom line. We should be celebrated, and we are. with Industrial Water Week, October 4th through 8th. Visit industrialwaterweek.com to learn more.
Nation, how are you going to celebrate Industrial Water Week? Well, the Scaling Up H2O team is going to help you out by giving you a brand new episode each and every day, starting on Monday, October 4th. That's my anniversary, by the way. 25 years. Wow. Anyway, that's not what we're talking about. We're talking about Industrial Water Week. So with that, I can't wait. I can't wait to celebrate every single day with you. What are you going to do for Industrial Water Week? You know, now it's time for one of my favorite things, and that is answering questions from you, the Scaling Up Nation. So here's a question.
Hey, Trace. Was recently revisiting some of the Scaling Up archives, namely some Pinks and Blues episodes that focused on topics around water treatment fundamentals like pH and alkalinity. One topic I thought would be beneficial for me and the nation is an episode dedicated to cycles of concentration or concentration ratio. You're the host, so I guess whichever term you like better is the one you can go with. It'd be helpful to hear, ideas around how concentration ratios are determined in both cooling and steam applications, maybe why certain ratios are targeted, why is it important to our clients and to us as water treaters, and in what ways are we able to influence cycles of concentration. Thanks in advance for the help.
Well, caller, thank you so much for that question. This is a topic that most water treaters think is very easy. And I really want you to think about whenever you think something is easy, it's probably the hardest thing for you to explain to somebody that does not have the same common knowledge that you do. Einstein once said that if you cannot explain something to a 5-year-old, you don't understand the topic. There's so much wisdom in that statement. And I really think when it comes to whatever we call it, cycles of concentration or concentration ratio, there's so much going on there. We kind of deal with it every day, so we think it's simple. But when we explain that to somebody that doesn't understand it, a lot of us don't do a great job. And let's talk about the fact that we have two different terms that explain the same thing: cycles of concentration and concentration ratio. Well, anytime where we have two terms to explain the same thing always complicates the issue. And we're going to talk about that. But first, let's talk about what it is. The way I explain it is only pure water evaporates, leaving its solids behind. We cannot leave the device, the cooling tower, the boiler, to run dry, so we need to add more water to that. We call that makeup. Well, that makeup also has solids in it. So in addition to the solids that were left behind and the water that we evaporated, we're now bringing on additional solids with the new volume of water that comes into that space. Well, as it evaporates, it leaves its solids behind, and we start concentrating how many solids are in the system. So knowing what that is, I really think that concentration ratio explains what we're trying to say. So I prefer the term concentration ratio because it explains itself. What is concentration ratio? Well, it's how many times the system has concentrated itself. Well, now if I call it cycles of concentration, and I say, well, what is cycles of concentration? If we define it that way, somebody's going to say, well, it's how many times the water recirculates. I cannot tell you how many times I've had customers think that that's what it is, even after we did some sort of presentation explaining what concentration ratio was or cycles of concentration was. Take it from me, it's so much easier to use terms that define themselves. I think concentration ratio makes your life a lot easier. One of the ways it makes your life easier is now your customer understands why you're doing some of the things that it is that you are doing. I know if you have been in water treatment for any length of time, you have had a customer shut off the bleed of your cooling tower or your boiler because they did not want to waste water. Now, if you don't understand what we just talked about, that makes perfect logical sense. Oh my gosh, there's water going down the drain. Water's a valuable resource. I must stop that water from going down the drain. Now, for everybody listening, we're all in the know because we understand that we are diluting out that highly concentrated water with lower concentrated water, 1 times concentrated water, the makeup water, so we can use that water to its fullest ability. Now, when that customer thought they were saving money, saving water by turning off that bleed, they now allowed that system to over-concentrate. And we had that system set up so only so many cycles, only so many ratios would take place because we know eventually certain ions are going to come out of solution. And when they do, they form scale. And we are all heat transfer efficiency managers. You've heard me say that on previous podcasts. And if we do not have a clean surface, we are not going to be able to efficiently transfer that heat from one area to another. That means the system has to work harder. That means we have to spend more money buying electricity to overcompensate for that dirty system. So the 3 cents that our customers saved on water probably cost them $12,000 in extra electricity, and it's going to take us months to clean that off the system. All that to say, when we are able to let our customers know why it is we do what we do and explain to them the things that they're going to see around the mechanical room because of the things that we did, show them what's normal, explain to them why we're doing what we're doing, you're going to have less issues. And if you have less issues, you have a happier life, you have a happier customer, and you're going to have a long-time customer. So all of that because we're now going to adopt the term concentration ratio. Well, let's go ahead and start with math around concentration ratio. And of course, in order to do that, we have to do a mass balance. A mass balance is a really fancy way of saying that water in equals water out. We have to put water into the cooling tower, and that's makeup, and the water that leaves the cooling tower, we have to replace so it doesn't run dry. Now, how does it leave the cooling tower? Well, it leaves in 2 different ways, either evaporation or bleed. Now, the same principles work with the boiler as well, but the equation I'm going to share with you is for cooling. And boilers, actually it's the same equation, but you go about getting them slightly differently. I'll do that one on a different show. We'll stick with cooling today. So here's some math. So if you guys are driving, take a sip of coffee. I know some people instantly fall asleep whenever they hear math. I don't want anybody to put themselves in danger. So if you are one of those people that can't handle math and driving at the same time, please stop doing one of the 2 things. One, driving, or listening to this podcast. I'm going to prefer that you stop driving because who would want to turn this podcast off, right? Here we go. The evaporation equation is 0.001 times the recirculation rate times the temperature differential across the cooling tower times a heat rejection factor. All right, so one more time, 0.001 times the recirculation rate times the temperature difference across the cooling tower times a heat rejection factor. And that's going to give you evaporation in gallons per minute. Now, let me explain a few things here because I want to define everything as we go along. The first thing I gave you was 0.001. Well, it takes 970 BTUs to evaporate a pound of water. We're going to round that up, be very simple, and we're going to say it takes 1,000 BTUs. So 1 divided by 1,000, that's 0.001. That's where that comes from. Next up is the recirculation rate. Now, recirculation rate is tonnage times 3. If you want an explanation on that, please go to episode 128, where I did an entire show on tonnage times 3. So the temperature difference across the tower, all that is the difference between the hot water coming in on the top of the cooling tower versus the water that has been cooled at the bottom of the cooling tower. Whatever that difference is, that's the number. And typically, by design, that's 10 degrees Fahrenheit. And then finally, there's this heat rejection factor, and that's going to be different depending on where you live. Here in Atlanta, we typically use a 0.85. Now, depending on if you're in a wetter or drier part of the country, that is going to change. Probably do a whole show on that, but I'm willing to bet that your company has those parameters set up depending on where you're working in the world. Now, for fun, when we do equations, we're going to just use that at 100%, just so you can see the differences. And I know they're going to be a little bit different depending on what your area is, so that's why I've decided to just use that one factor. So let's now do some math. So let's say we have a 1,000-ton cooling tower. And we went ahead and we measured, and the delta T, or the difference across the tower, is 10 degrees. Again, 10 degrees by design. And we're just going to use a factor of 1. We'll say that all the heat is being rejected. Now, keep in mind that normally never happens, but for this example, I just want to make it easy. We're just going to leave that as 1. So essentially, I'm setting up the equation, 0.001 times the recirculation rate, which is tonnage, 1,000 times 3, which is 3,000, times our temperature differential, which is 10, times our factor, which is 1. If we do the math, our evaporation is going to be 30 gallons per minute. Now, how much is that per day? Well, per day, we would just multiply our per minute rate by 1,440, the number of minutes in a day, and we get 43,200 gallons a day is what is being evaporated. Now, let's go ahead and calculate bleed. Now, the calculation for bleed, very simple. It's the evaporation that we just figured out divided by whatever concentration ratio we are running minus 1. Why is it minus 1? Because you always have a volume of 1 in the system. So if we were to do the math, we would have 43,200 divided by, and whatever the concentration ratio is, minus 1. So if we were running a once-through system, then what that would mean is we were also bleeding 43,200 gallons of water. So our makeup has to be double that, and that means that our 1,000-ton cooling tower will be making up 86,400 gallons. So as we can see, that is a lot of water, and that's why we don't do a once-through system. So normally, that allows a water treatment professional like you to come in and figure out all the things that are in the water, which ones are going to scale first, which ones are going to precipitate first, and that first precipitating ion, however many times you can concentrate that up, that's going to be what's called your limiting factor. So let's say, for example, it was silica, and we can only concentrate silica up 4 times. Typically, we use 150 as the top range of silica. We'll say it has 50 ppm in there. We can only concentrate that up 3 times. Well, we probably don't want to test that limit, so we're probably going to back that down a little bit. And that means that our top concentration ratio is going to be 2 point something, whatever you feel comfortable with. And we probably have a polymer in there to help us with silica. I don't know if that was the best example or not, but I think you get where I'm going. Whichever ion we're going to get to first, that's going to be our limiting factor. So with that, it's very important for us to understand what it is that's going to be our limiting factor, how many times we can concentrate it up, and is there something we can treat that limiting factor with? For example, if it was calcium, then maybe we can soften the water. And now we can get a higher concentration ratio. Maybe we could use a special product to extend how much that specific ion can stay in solution, and now we can concentrate the water up higher. So every time we graduate to another concentration ratio, we are saving some water. And let's look at that. So if we were a once-through system, going from 1 to 2, well, that is a 50% savings on water. And how do you figure out how much water you're bleeding? It's really simple. It's the reciprocal of whatever your concentration ratio is. So if I'm at a concentration ratio of 3, I would just do 1/3 of the evaporation. And that will allow me to figure out how much water I am bleeding out. Now, I got this question at one of the math events that I do for AWT, and somebody wanted to know, well, how was evaporation changed by how many times you concentrate a system? And evaporation does not change. That's the constant through all of this. What changes is your bleed, and that gets me to makeup. So makeup equals evaporation plus the water that's bled out of the system. And hopefully through the demonstration I just gave you, you can see that the higher you concentrate the water up, the least amount of bleed that you are having. And logic dictates that the more you can concentrate up the system, the world is happy, the sun is shining, rainbows are out, birds are singing. We just concentrate that sucker up as high as we can go because we're saving water. Well, here's the thing. Remember, I just mentioned the reciprocal. So concentration ratio under 1. With that, if you do the math, 1/2 is huge. That's the largest amount that we're ever going to get. Well, 1/3, that's still a lot of water. 1/4, that's a good amount of water. 1/5, 1/6, 1/7, 1/8, okay. 1/9, not that much movement between 8 and 9. Between 9 and 10, even less, and higher than that, there is such a minute savings in water when you start pushing the limits up that high. Normally, it is not worth it because what you're doing is you are concentrating things up so high, you're probably really stressing the system out. Some of the products you have may not be able to keep all those ions into solution, but something that's happening that a lot of people don't realize is you are creating such a viable food source for all of these bugs, all these microorganisms to come in and have a buffet in your system. You're really going to diminish your heat transfer capacity because now you've got organic fouling throughout your system. Now, maybe you can offset that with a bunch of biocide, but is that worth it? And how much is that biocide costing versus how much are you saving in water? Now, maybe there's a reason to do that. You're the professional water treater that's on site out there. You can answer that a lot easier than I can because you have firsthand knowledge of what you're trying to do. But if you're just doing that to try to save water, you're probably not saving the amount of water that you think, and you're definitely making it so incredibly difficult for you to control the organics in that system. You know, something you might be wondering after that conversation is, how do I verify that things are staying in solution? And I'm going to be honest, some things are easier than others to work a ratio out. So just like we did a ratio with concentration, we can do that with the water that we start with versus the concentrated up water and see how many times, in theory, it should have concentrated up. Now, a lot of us do that with chlorides. Chlorides is a non-scaling ion, and we will take the chlorides in the raw water and we will take the chlorides in the concentrated up tower water, and we would divide one into the other. And whatever that equals, that will tell us how many times we've concentrated up that water. Now, a lot of us are using chlorine, sodium hypochlorite. Well, chlorite sounds like chloride, so that's going to interfere with that test. So you might not be using that. So something else you might be doing is maybe you're doing hardness. You're looking at the hardness in your raw water, and then you're looking at the hardness in your concentrated up water, and you're seeing what the ratio is between those. How many times have you concentrated that up? Now, if you're softening that, well, of course, you can't do that either. Well, here in Atlanta, we normally don't have a silica problem. We do have some wells that have some higher silica, but we use silica 9 times out of 10 to determine what our concentration ratio is. So we will take the silica in the raw water, we will take the silica in the concentrated cooling tower water, we would divide those out, and we would find that we have a concentration ratio of X. And in Atlanta, it's normally around 8 or so. Well, if we were to determine that, let's say for example's sake, that it was 8, well, we should, in theory, find that every ion that we test should be 8 times that from what was in the raw water that is now in the concentrated system water. So if we were to do chlorides and chlorides was able to work properly because we weren't using chlorine, we should find 8 there too. If we were to do calcium and we weren't doing a water softener, we should find 8 there too. Now, in theory, we should be able to do the same thing for alkalinity. However, you are going to lose some alkalinity across the cooling tower. Don't believe me, take a sample from the incoming tower water and the leaving tower water, and you will find that there is a slight difference. So when you start understanding all the different things that you're supposed to be keeping in solution, and then you start running ratios to see if you're actually keeping those things in solution, you don't have to guess what's going on in the system. You can actually prove what's going on in the system. So let's say I had that, let's use 10. I don't know why I used 8. And most of us probably can't get as high as 10, but it's easy math. And let's face it, you guys are driving. We need some easy math. So let's say you have a calcium hardness of 10, and you can concentrate that up 10 times. And let's say we've done that, we're going to expect to have 100 parts per million of calcium hardness in the system water. And we verified that there are indeed 10 concentration ratio in that system. Well, let's say it comes back and it's 60. Well, what's going on there? Well, if we're getting less, and if it's just a little bit less, it's probably just because things change throughout the day. It hasn't always been 10. Maybe it was 9.8 at one time. So things change a little bit. If it's slightly off, I wouldn't worry too much about that. I would run some other tests to confirm that. But for all in all, you don't worry about slight changes. But let's say it's supposed to be 100 and now it's 60. Most likely, that is telling you that one, somebody installed a softener on the system and you didn't know about it. Two, you are losing that somewhere. So it's no longer dissolved in the system. And that's what's happening when you do a test. You are testing dissolved solids. Well, something precipitated out. It's not dissolved anymore. That's why you can't test for it. Where did it go? Well, in that case, I would test your alkalinity as well. I'm pretty sure that's going to be lower than it should be, even with the cooling tower phenomenon that I just mentioned. Where did it go? You formed calcium carbonate, and that is a telltale sign that you have scale in the system. Well, let's look at the inverse of that. Let's say you test it and it's now 150. So we're getting a concentration ratio of 15 on calcium hardness, but we're only running a concentration ratio of 10 in actual. What's going on there? Well, we figured out we had a problem. We fixed the problem, and now we are redissolving calcium carbonate back into the water. We're dissolving that, and there's the proof. And in that situation, you'll probably have a higher alkalinity as well. So think about it. You've got all the tools in your test that you need to figure out what's going on in the system. If you know what test you have and you know how to run those tests and what they are telling you, you can apply that to your concentration ratio knowledge and have deeper knowledge within the system. And nation, there are so many things out there to try to conserve water. You've probably seen some things that people are doing. Perhaps you're even maintaining some of these things. What are these things? Well, you might see reverse osmosis on cooling towers. And what they're trying to do, they're trying to reduce the amount of solids that we start with so we can continue to concentrate that water up a lot more than if we were just using regular city water as the makeup. You might see electric deionization. They might be using some sort of deionizing. Maybe there's a resin bed in there. I mentioned earlier water softening. So there are all these different things that we can do to reduce the ions that are going into the water so we can concentrate them up more. The bottom line is there's only so much water on the planet. I've said this on the show before, but in the United States, we are so incredibly fortunate that we never have to worry about turning a faucet on and if water is going to flow out of it. And nation, there are many parts of the world where they don't even have a faucet. They have to walk. I think the average is 6 kilometers. They have to walk to and back to get drinking water. So think about how fortunate we are in this country or in other parts of the world. Not everybody is that fortunate. So as an industrial water treater, we have a duty to protect all the water that we have on this planet. and to make it so it is as easy to find, as easy to use as possible. And when we can reduce the amount of treated water that's coming to us in the systems that we're responsible with treating, we can make a dramatic impact, a huge impact. I would argue that the industrial water treater can save more water than pretty much all the other professions combined. We have a tremendous opportunity here. Now, you might be thinking, Trace, we've got the same amount of water on this planet as we did when this planet was made. And you know what? You're right. And if you were to look at this planet, you'll probably also say, Trace, there are 2/3 the amount of water on this planet to the 1/3 of the amount of land that we have on this planet. So how could we possibly have a water shortage? Well, when we look at the water that's readily available to us, that 2/3 of our planet that is water, it's water that's not readily available. So it means that we have to do something to it. And most of the water is in the oceans. And desalination takes a lot of equipment. It's very expensive, and there's a lot of waste for every good gallon of water that we make. Not to say we can't do it, but it doesn't fit our definition of readily available. So if we look at all the water on the planet, most of it's in the oceans. And then the fresh water that we have, most of that is in areas that we can't get to, or it's very difficult to get to. So if we were to look at all that water on the planet, less than 0.5% is really the amount of water that we have that's readily available to us. We've had that same amount of water since the beginning of our planet, but what has changed is how we use water. We are using water in every single process that we have, and we're using it more and more every single day. So when a profession like ours is able to really be responsible with the amount of water that we use and how we send that water back to get recovered, we can truly make an impact. And when we understand basics like concentration ratio and the different ions that we need to look for to prevent scaling in a system, what we can do to extend the solubility of those ions so we can use that water even more. And then we explain to our customer how we've done all those things and what a normal operating condition looks like in their mechanical room. We're all working together, and we are making sure that there's enough water to go around. I want to thank that caller for this question. I got to tell you, when I was doing notes answering this question, there are about 40 other things that I want to talk about, but this is an hour or so long podcast. I try to keep them around an hour or less. So I have so many other things to cover with this. And with me saying that, you have so many things to explore around this. I know some of these things I said you probably already knew. I'm hoping some of the things I said got you thinking about what you do on a day-to-day basis. And you're thinking, wow, I can probably explain that a little bit better. So the customer understands what I'm doing. The customer understands my value better. But then I can also explore ways that I can do better. So whether it's one or all of those, I hope I inspired you to do something. And speaking of inspiration, if this guy doesn't inspire you to go one notch further, I don't know what's going on. Here's James.
Hello, Scaling Up Nation. The next James's challenge as we grow as an industrial water treatment professional, drop by drop, is ask a colleague to audit your water systems. We can all be too close to a topic and miss glaring errors right in front of our faces. It can also take a level of bravery to suck in our pride and ask for help. But if you have the opportunity to do this, having a second set of eyes on your water systems can be a win-win for everyone. Be sure to share your experience on LinkedIn by tagging it with hashtag JC21 and hashtag ScalingUpH2O. This is James McDonald, and I look forward to seeing what you share.
Nation, this is one of my favorite things to do, and I've made a career out of this. I consult with other water treatment professionals, and one of my favorite things to do is play a game called Let Trace Blackmore Steal Your Business. It's all fun, it's all make-believe, but what I do, I don't actually steal the business, but I do go in as if I were. And I look at all the things that should be done differently and basically find all the cracks in the account and then let the person who brought me in know what those are. We work together so they can fix all those items. And I will tell you the truth, sometimes those items they fully are aware of and they've talked to the customer about, but the customer does nothing. Now, Nation, I know that you have lost a piece of business because you told a customer that they needed to fix something, they didn't fix it, and then a competitor came in, said the same thing, maybe even they gave away a little bit of equipment to help them fix it, and now you lost the business. So don't let that happen to you. Ask a colleague, what are they seeing that you don't see? Maybe it's something that you saw a long time ago and now you're immune to it. And if it's something like that, maybe you two can brainstorm and figure out how you can speak to the customer so they understand why they need to change it. And now they're actually motivated to make a change. By the way, when customers don't change something you want them to change, it's because they don't understand why, and the pain of changing it is greater than what will be relieved if they fix the issue. That means you didn't explain it right. If it pains you and it doesn't pain them, just like how we explain concentration ratio, you need to explain that issue differently so they can feel the pain just like you do. And I promise, if you learn how to do that, they're going to fix that issue and everybody's going to be happier. You know, another thing that would make me happy is for you to tune in next week for a brand new episode of Scaling Up H2O. Take care, everybody. Scaling Up Nation, life is too short to do it alone, and that's why I have been in a mastermind for over a decade. It's why I started the Rising Tide Mastermind, and it's why the Rising Tide Mastermind is so successful. You do not need to face your problems alone. You don't need to face your issues alone. You can learn from others' experiences so you don't have to repeat their mistakes, and you can get further faster because others are giving you a hand. To find out more, go to scalinguph2o.com/mastermind to see if this is the right group for you.